Okay, good morning. So let us start the lesson as far as we can do it here on this very small board. So if you remember, we talked about the determinant of a matrix. So if A is an n by n matrix, a square matrix, we can talk about the determinants of A or by this symbol. What is the meaning of that? If you remember, we defined this recursively. We first started talking about the one by one determinant. So if you have a matrix with only one entry, if I ask you what is the determinant of a matrix with just single entry A, we define it to be A itself. Yes. And then we uh, wrote a formula for defining an n by n determinant. So if A is an n by n matrix, so if you calculate this determinant, if you want to calculate this, it means that you take A11 and then what we introduced as the cofactors. So C11 and plus A12, C12, and then you continue until A1n, C1n. Yes?
Shouldn't the cardinality of A be 1?
Pardon? There is no meaning of cardinality for matrices.
What do you mean? Okay, sorry. What
This
do you
means
mean?
determinant.
Okay.
Because for determinant we have two symbols.
Oh.
Yes, if you don't like it, we can write determinant.
Thank you.
And then I don't want to repeat everything, but from this we learn that if I have a 2 by 2 matrix, A, B, C, D, we learn that if you want to calculate the determinant of this, sometimes simply people show it with this symbol without having a square brackets. You use the square brackets for matrices, and that's just parallel lines for determinants. So sometimes people show it using this symbol, sometimes more compactly like this. We learned from this formula that for a 2 by 2 we have a simple formula, and that is AD minus BC. That I really recommend you to have it in your memory for a 2 by 2 determinant. But for 3 by 3, 4 by 4 determinants, there is no point if you want to remember the formula or something. It's better to learn how to do it. Yes. So let me remind you of what are these. So for example, let me calculate a 3 by 3 determinant. So I would say that 5, 2, and 1. So let me make this one 0 to make it a little bit simpler. And then you have 2, 1, 1, 3, minus 1, minus 1. For example, you want to calculate this 3 by 3 determinant. Okay, we use the original formula. Okay, so what you do, you take the entry first, the entry on the first row, first column, which is 5. Yes, and you multiply it by C11. Yes, then plus 2 multiplied by C12, because this is the entry 1, 2, C12, and then plus 0 C13. So for the time being, immediately, regardless of what number is that last number, you know that the answer to this part is at least 0. But what do I mean by C11? Do you remember? C11 starts with a factor of minus 1 to the power of 1 plus 1. But what you do, you go to the entry 1 by 1, 1 and eliminate that column and eliminate the column and the row containing that element, and then you see that you will get a 2 by 2 block, and then you calculate the determinant of that 2 by 2 block, which is 1, 1, minus 1, minus 1. How? Recursively. So when you want to calculate a 3 by 3 determinant, you have to know already how to calculate a 2 by 2 determinant. So it is needed here. Okay, so let us just do this simple calculation. This is just simply 1, and this is minus 1, minus 1 plus 1, it is 0, yes? And I also calculate C12. I should do that? I write minus 1 to the power of 1 plus 2, and then a 2 by 2 block. a 2 by 2 determinant. How can I get it? I go to entry number 1, 2, which is this number, and then I eliminate the column and the row containing that. Then I have 2, 1, 3, minus 1. And then I calculate this. Minus 1 to power 3 gives me a negative sign. And then 2 times minus 1 is minus 2. Minus 3 times 1 is minus 3. So finally the answer becomes 5. And then when everything is ready, you put it back into this. So what do you get? You get 5 times 0 plus 2 times 5 plus 0, and the answer becomes 10. Yes? So that's how we calculate the determinants. So something that I told you, even though this is the definition of a determinant as I taught you, but this is called expansion on the first row. So if you calculate your determinant using this particular formula, at the end you can say I calculated the determinant by the expansion on the first row. But that was a hard theorem. I didn't prove it at all for you, but I told you as an information. I want you to know that. So you can do the same thing on any other row or even any column. The results will be the same. For example, let me check it out for this second column this time. Okay, so if I want to calculate that determinant, so the question mark, this is entry number 1, column 2, so it becomes A12, but then you have to multiply it by the cofactor 1, 2. And then when I go to the next one is the second row, second column, so it is A22, and then you have to multiply it by C22, and then I go to the next one, which is the third row, but the second column I multiplied by C32. So these indices are exactly the same indices here. So for computing a determinant, first you have to decide on which row or on which column you want to do the expansion, and then it doesn't matter, you will get the answer. So it is clear that which one is better. For example, this was not a good choice that I did here. A better choice was, for example, the third column, because it includes a 0. And if it includes the 0, you see that I don't need even to calculate this coefficient, so it is 0. So it is always better to expand on a row or a column which includes more zeros because of simplicity in calculations. But at the end of the day, it doesn't matter. Okay, so let us check this one. So here, let me calculate these 3 numbers first. So C12 means what? I have a factor of minus 1 to the power of 1 plus 2, and then I have a 2 by 2 determinant. How I get it? I go to this entry, eliminate the row and column of that. So what is left for me is 2, 1, 3, minus 1. 2, 1, 3, minus 1, which coincidentally is exactly the same as here. I have already done that, so it becomes 5. And then I go to C22, yes? So it's minus 1 to the power of 2 plus 2, and then I have a block, 2 by 2 block. How should I find that? I go to this entry, and I eliminate this row and this column. So 5, 0, 3, minus 1 is left. And then I calculate that. This is an even number, so it is just 1. So it is 5 times minus 1, which is minus 5, and this one is 0. And finally, I go to C32. C32 starts with the minus 1 to the power of 3 plus 2, and I have a 2 by 2 determinant. Okay, so here, what happens here, it becomes, I go 3, 2, 3, 2. I eliminate that, so what was left? 5, 0, 2, 1, yes. 5, 0, 2, 1, and this is a negative one because it is odd, and this is 5 minus 0, 5 minus 5. Yes? Okay, so let us see if I haven't done any mistakes. So I go back there, that the question mark is equal A12, 1, 2 is 2, multiplied by C12, which is 5. A22 is 1, multiplied by C22, which is minus 5. and then finally plus a3 1 is minus 1 multiplied by minus 5. So let us calculate. So this is 10 minus 5 plus 5. Yeah, so it is 10 again. So you see that it doesn't matter. Okay? And I actually do it a little bit quicker than writing all this mess. So if I want to calculate this myself, I prefer to do it in this way. I also recommend you to do it like this. So first of all, decide about a row or a column. For example, you decide about this column, yes, because it contains 1, 0. What I do, I assign a sign to it. So for example, I start here. This is the first row, third column. If I add them, it is even. So I give a positive sign in my head to this one, and I don't need to care. When I go one step ahead, then it becomes negative, then it becomes positive again. Do you agree with me? Because I'm keeping the column number the same, but I'm adding one row number. So alternatively, it becomes even and odd. So if the first one is positive, meaning that this is even, the next one definitely is odd, the next one is. So I assign something, some symbol like that, some sign like this on top of my head, and then I will do this. So I will write 0, and of course multiplied by any determinant, I don't care. And then when I want to write this, I don't write 1 here, I also include this sign that I already put there, so it's minus 1. And then what I do in my head, I eliminate these two, 5, 2, 3, minus 1, yes? 5, 2, 3, minus 1. And then I go to the next one, it is minus sign here, but this sign is positive, minus positive is minus. And then what I do, I eliminate this row and that column, 5, 2, 2, 1 is left. 5, 2, 2, 1 is left. So what happens? So this is 0, whatever it is. So this becomes minus 5, minus 6. What is that? Minus 5, minus 6, minus 11, and that becomes positive 11. And this is 5 minus 4 is 1, it is minus 1. So again, as you see, the answer is 10. So that's it. So you need to know how to calculate the determinants like that. Okay.
Could you do that method one more time?
What?
That method.
This method?
Yes.
So first I decide on which row and which column I want to expand. So let us say I assume I want to expand on the third column because I have some 0 there. And then I start assigning some signs here, because you know that these cofactors, it starts with a symbol of this, yes?
Mm-hmm.
And something like that. And this means that this number is either plus 1 if this sum is even, or minus 1 if that sum is odd. So I only calculate evenness or oddness of the first one.
Yeah.
So this is the first or the third column, so 1 and 3 added is even. Even means that I have a plus sign there. So I assign a plus sign or in written form or in my head, but as soon as I find one of them, it is clear that when I go down or left or right, this will change alternatingly. Because if I go down, I am keeping J the same, the column the same, but I am increasing I once at a time. So this means that if this is even, the next one is one more odd, the next one is even again, etc. The rest of it is a... Okay, so, and then I told you that calculating determinants by this definition is a very complex computational problem. So if you want to calculate, if I'm right, if you want to calculate a 30 by 30 determinant by just a very fast PC that you have, by this method, it will take more than 10 billion years. Okay, so this is actually very, very inefficient way of calculating determinants. So this is why we want to learn more tools in our hands. So the method that the applications use to do this is LU factorization of a matrix. So if I give you an n by n matrix, so you can always write that matrix as a product of a lower triangular matrix and an upper triangular matrix. But calculating the lower determinants of triangular matrices are extremely simple. That would be one part of our lesson. I don't think we have covered that yet. So this is the most efficient way of calculating the determinants. So this is more or less what we had before. Of course, we solved more examples, but the ideas in those examples are all the same. Okay, so at least you are motivated. But for example, if I have a 4 by 4 determinant, what happens? In principle, if I want to calculate that determinant, I will have 4 3 by 3 determinants. Yes, because what I do, I write A11 and C11. For a 4 by 4 determinant, C11 is obtained by eliminating one row and one column. My matrix is 4 by 4, so in that case it becomes 3 by 3. And how many of them I will have? I will have 4 of these 3 by 3, and every 3 by 3 determinant is calculated using 3 2 by 2 determinants. Yes? Yes. Yeah. Yeah. So okay, so this is, so how many determinants in principle we have to calculate if you want to understand that. So for this one I have 4 3 by 3, and for each 3 by 3, yes, I have how many? I have 3 2 by 2, okay, and then it becomes more or less 12 determinants. Yes. Okay. So you see that this becomes quite heavy in calculation. So that's why it is a good idea to think about some shortcuts if possible. For example, I think we talked about that before. So assume that I have a matrix with one fully zero entries. Do I really need to calculate the determinant of that matrix? So for example, if I ask you, how can you calculate this? A, B, C, D, E, F, 0, 0, 0. You really don't need to calculate anything. Of course, you might make trouble for yourself by expanding on the first row, but I told you it is not needed to do that, so we prefer to expand it on the last row. And then what happens, this becomes C, 0, C1, 3, 1, plus 0, C, 3, 2, and plus 0, C, 3, 3. I don't even care what these numbers are, because finally the answer becomes 0. So, and it doesn't matter if this is a row or it's a column. So as soon as you have one complete row zeros and or one complete column zeros, the determinant is 0. Is that clear? Okay, but another theorem that I just mentioned is this. It's a very interesting theorem. So if I give you let us work with 3 by 3. Because if I want to write all the details, it would be time consuming. So let us assume that I have a 3 by 3 matrix, but let us say lower triangular matrix. So what does it mean? It means that I have A, B, C, D, E, F, but these are 0. There is a very nice relation. You really don't suffer at all to calculate the determinant of such a matrix, even if this is 1000 by 1000, yes? The answer is very simple. The answer is just multiply these numbers, ACF. So the entries on the main diagonal. So the answer to this is ACF, okay? If you want to see why, of course, you can prove it using mathematical induction, okay? By increasing the dimension of your matrix. So you start from a 2 by 2 matrix, you say that, okay, look, for 2 by 2 matrix it works. Let us assume that it works for a k by k matrix. We can prove it works for a k plus 1 matrix. Okay, but I want to skip those things because that's not hard. But let us try to understand that. For example, if you want to calculate this determinant, assume that you don't know this rule, but I want you to use this rule effectively later. Yes? So if you don't know this rule, which row or which column you prefer to start with?
The first row.
For example, the first one is actually quite good. The last row is also column is also good. So how can I calculate? I would just write A and eliminate this row and this column, and this is left. And then, of course, do I need to write the other ones? No, because 0 whatever, 0 whatever. That's it. So what happens? If you look at here, this is also a lower triangular matrix. So that's why induction works. So if you start with 3 by 3, use this rule once, you will face up with what? With a 2 by 2 triangular matrix. Okay, of course, if I continue this, A is just A, and you know that if you want to calculate this, you just multiply these two, subtract them, but this is just CF. Okay? So this, I want you to know that if you have an upper by the way, this is also correct for an upper triangular matrix. So this I cannot show you on the projector today, but this is the theorem 2.2 in the lecture notes, yes? 2.12. So this is the determinant of a triangular matrix. I haven't mentioned the adjective upper or lower, is equal to the product of the entries on the main diagonal. So this is one thing I want you to know. For example, these are also very important to know. Can you tell me what is the determinant of the identity matrix? By the way, I talked about upper and lower triangle. What about the diagonal matrices? So if I give you a matrix like this, D1, D2, D3, up to anywhere you want, but everywhere here is 0. This is a diagonal matrix. What do you think will be the determinant of this matrix?
Maybe the same rule.
The same rule, because a diagonal matrix is simultaneously upper triangle and lower triangle. So that's also working for diagonal matrices. Yes? So, and then you immediately can tell me what is this one? 1, because the entries are all 1. And of course, this is very ridiculous to ask. What is the determinant of the 0 matrix, square matrix? Of course, 0. Everywhere is 0. Yes? It's good to know. Okay, there is one more thing. It's not that trivial.
I'm sorry.
No worries. But your face might be appearing here. If you want, I can pause. Wait. Okay. So the next theorem is a very nice theorem. Let us start with this idea. So for example, I give you a matrix. Let us start with 2 by 2. By the way, I hope that you understand what I say about a 2 by 2 matrix. It is not automatically clear that it will extend itself over 2 by 2. Yes, because the formulas of the determinants are become extremely complicated when we go to higher orders. So whenever something is true for a 2 by 2 determinant, there is no guarantee that this is also true for higher order determinants, okay? But it is a good starting point to understand what I mean, okay? So A, B, C, D, this is one matrix. But what I do, I pick a row or a column and multiply the entries of that row or column by just a fixed number, say R. So for example, I choose the second one and I multiply the entries of the second one by some constant number R, but I leave the first ones intact. And the question is that, is there any particular relation between the older determinant and the new determinant that I want to generate? And the interesting is that yes, there is a relation, and this relation can be extended over 2 by 2 determinants to any order determinants. Okay, what is the connection? It's very extreme. It's easy in this case to discover. Yes?
It's just R and then the determinant.
Yeah, why is that? Because if I ask you to calculate this, you just simply calculate AD minus BC. Yes? And if I ask you to calculate this one, you just do the same thing. Yes? It becomes RAD minus RCB. But what can I do? I can factor an R out. It becomes AD minus BC. And then you see that this is your old determinant. This is your new determinant. What is happening? It's been multiplied by an extra R. Yes? But of course, you might say this is too simple. It works. How do you know that it works for a 3 by 3 determinant? Then some of them we can, by the way, prove. The proof is exactly what I want to describe, but I don't write it mathematically rigorous, okay, in a mathematically rigorous way. So let us ask you the same question. For example, I have a 3 by 3 determinant, A, B, C, D, E, F, G, H, I. So let us this time consider the column, the second column, and multiply it by a fixed constant number R. What do you think will be the relation between these? Of course, if I give you time, you can expand that one as well, and then compare the results. But do you expect that the same idea will also happen here? Do you think that this one is R times larger than this one because I have multiplied the second column by R? And if yes, why? Yeah.
If you just use the second column as and determine the determinant for that.
Expansion on the second column.
Exactly.
So it works. Do you agree? Because for example, let me assume that I told you it is independent on which row or column you choose to expand. In this particular case, we decide to expand on the second one, yes? So how do you expand that? Let us understand that. That's exactly the proof. but you have to write it in a little bit fashionable way, yes, mathematical fashionable way. So what you do, you just expand it over here. So tell me, I pick up this number, and I multiply it by what? I multiply it by, let me call this curly C, cofactor of which row? The first row, the second column. Do you agree? And then I go to the next one, plus the entry is RE, and then I multiply. I just tell you why I'm saying curly, because these two matrices are different, so in general might be the cofactors are also different. So let me just put curly C to represent the cofactor of that one. And this is just 2, 2. Do you agree? Because this is 2, 2. And then I go to the next one, it's RH, and I multiply it by the cofactor of the third row, second column. Do you agree? Okay, the point is that, of course, you can see I can factor an R out. I get this. But I hope that you agree with me, if I use curly C for cofactors of this, and if I use the normal C for cofactors of these cofactors are exactly the same. So for example, if I ask you, what is the cofactor curly C1, 2, what do? You find entry 1, 2, eliminate this row and that column. This block is left for you. Yes? And now go here and calculate not the curly one, just the normal one. Yes? So what do? You go to the first row, second column, which is B, not RB. But because you are supposed to eliminate these, so which block is left for you?
The same.
The same block. Okay? So of course, if you want to write it mathematically, you have to differentiate symbols. But then you should prove that, okay, every one of these curly ones matches with non-curly ones. So this means that I take these non-curly ones and take these curly ones and put the non-curly ones in. I hope that I could convince you about that. Yes. So this becomes R, and then I have B. Instead of curly C1 and 2, I can write C1 and 2, and I hope that you agree with me. You can check it yourself. This also works with the other cofactors. Yes. C H C3 2. Okay, but now if I ask you, what do you have here? What is your answer? This is B by C1 2 and E by C2 2, H by C3H. Do you agree that what I have written here is exactly this determinant? Okay, so I have also a factor of R here. So this means that I started calculating this determinant, and I realized that this determinant is R times that determinant. Is that clear? And then exactly like this, you can prove it. This works for all of them. Okay, so let me ask you one question. So it's by the way, it's very instructive to write it in this way that I want to write. So if I give you this, if I give you this A, B. So let me, for example, C, put R here. R, okay, let me put R the same position, not to confuse you. So R, R, E, R, H, and then D, F, G, I. So I hope that you agree with me. This determinant is R times which determinant? A, B, C, D, E, F, G, H, I. Yes? So we showed that one. But this is a nicer way to memorize it. It seems I am factoring R out. Okay? And because this is equality, it's extremely important to see it in both ways. If you have a common factor in all the entries on one column or one row, if you want to, you can factor it out. Okay? Be careful, it's very different from factoring out numbers from matrices. For example, if I give you this matrix 2, 4, 5, 7, and I ask you to factor 2 out from the first row, what do you write?
1, 2.
No, just read everything. This is a matrix, not determinant. I ask you to factor 2 out. What do you write?
Divide all entries by
Divide all the entries, not the first row, yes? It becomes 1, 2, 5 over 2, 7 over 2. Why was that? Because if you want to multiply a number to a matrix, you have to multiply it not just in the first row or the second row, you have to multiply it by everything. And that's a very big difference. This is sometimes I have seen it's a matter of confusion, okay? So when I put parallel lines, I don't mean matrices, I mean determinants, okay? And in that case, if I can decide to factor a number from the entries on one column or on one row. But in matrices, if I decide to factor a constant out, I have to divide everything there by that constant. But in this, yes. Now again, the other way around. If you see these 2 and you want to multiply it in, you multiply it everywhere. But if you have R here, what can you do? What can you do if it's going to be consistent?
Choose any row.
Any row or any column and multiply it back. So it's very interesting. So if you have it like this, you decide to factor it out. This is the unique way, more or less, of writing. But if you see an R here, you don't know where this R is coming from. Who knows? Might be this R is coming from the third column or it's coming from the second row. So if you have a constant there, that decision is yours. You need to decide about which row or which column, according to the problem at hand, you want to multiply it back. So for example, let us multiply it into the third column. It becomes A, B, C, D, E, F, or G, or H, or I. And then if you don't look in the middle, so you can say that I took R from here and multiplied here. So it works like that, okay? I don't mean this is wrong. I mean that you don't need to look at here and then you can. So in some case, if you decide for some reason to take R from here and put it on the third row, it is possible. Okay? Is that clear? It's a very, very important tool actually. So, but now let me ask you one question. So A is a 3 by 3 determinant, a matrix. R is a real number. So what I do, I multiply R by this matrix. It generates a new 3 by 3 matrix. And then I ask you how the determinant of this matrix is related to the determinant of the old matrix. Okay, think about it, okay, don't be in a hurry. How they are related. So you see, I give you a 3 by 3 matrix. You can imagine a matrix 3 by 3. You have a constant number R. You multiply R by your matrix. It becomes a new 3 by 3 matrix. So this means that I can ask what is the determinant of the new matrix. I can ask what was the determinant of the old matrix. There are 2 numbers. Do you think there is a good relation between these 2? Yes?
R squared A is the determinant of RA.
No, you get close but not completely. Yes?
Can't you just bring out the R?
No, that's the whole point.
Or R squared.
This is different. You said R squared, but I don't understand why R squared. R cubed. Yes? Because why? Because, for example, if I give you, be careful, this is a matrix, A, B, C, D, E, F, G, H. Okay? This is matrix A. Now, if I ask you what is the matrix RA, what is your answer?
RA, RB.
Everything, yes? RA, RB,
Okay.
RC, RD, RE, RF, RG, RH, RI. Yes? Now, if I ask you what is the determinant of RA, what can you do? You can write it as this parallel line, RA, RB, RC. Let me just write everything, be patient, yes? RF, RG, RH, RI. Do you agree?
And then you bring out the R.
So you can factor 1 R from the first row, okay? So if I bring that R out, these are not affected. They will be left the same. And then I decide bring another R from the second row. Then I decide bring another R from the last row. So it becomes R to the third. And then what is left for me? A matrix without any R's at all, yes? Yes? And then what is this guy? This is just the determinant of my original matrix. So this becomes R cubed, the determinant of A. So that's extremely important. Don't get confused. I don't know. This is a simple fact, but people get confused. It matters if you are multiplying a constant by a matrix or you're multiplying a constant by rows of the determinants, yes? So now can you tell me in general what will happen if I give you an n by n matrix and I multiply it by a constant r and then ask you how the determinant of this new matrix is related to the old one? What's the answer?
R to the n.
R to the n. Yes? Okay. So if I want to design a question for you so that it matters, I have to give you the order of the matrix involved. So I have written a bunch of calculations, random calculations, but I want you to understand this idea a little bit better. So let me just repeat it, because I don't have projectors to show that. So let me just write it. It doesn't take that much time. I'm not doing these calculations towards a particular goal. I'm just doing them randomly so that you can see they are valid. For example, do you think I can write this like this? I have a 3 by 3 determinant. 652. Hopefully I haven't mistyped anything. Let us check. Do you think I can write it like this? Is that okay with you? So if you see this relation, of course you can calculate this, calculate that, and see that this is correct or not, but there is a faster way to understand that. Is it correct or not?
Yes.
Yes. So what you have done, you haven't touched the first row, you haven't touched the last row, but you factor the 4 out. Yes? But what do you think? Can I write this as 4 times 2 and then write 131, 164, and 352? Is that also okay with you? So if someone tells you that this determinant is 8 times larger than this determinant, do you agree?
Yes.
Yes, but this time I decided to factor a 2 from the first column. So that's correct, yes? And now I write it like this. 8, let me copy and paste everything here. And then, for example, I write it like this. 1, 3, 8, 1, 6, 32, 3, 5, 16. Do you agree with that one? Yes, because now I decided to multiply 8 in, but I'm not allowed to multiply in every entry. I have to decide about a column or a row to multiply it back. And I decided for no reason, by the way, I just multiplied that there. But might be it is not that easy to see that these two determinants are identical. But you need to do some gymnastics like this to go from here to there without expansion. Yeah? So in principle, we are able to show that. Have I miscalculated something or not? No, good. So this means that this matrix is the determinant of this matrix is exactly equal to the determinant of this matrix, even though some of the entries are not the same. But we can guarantee that by this theory. Yes. So when I was at your age, our teachers used to torture us by these kinds of questions in the exam. I liked them very much, but I remember that it was very stressful during the exam because you need to discover. It's like a game. For example, I mean, I also see a lot of these kinds of questions in Indian books, yes? So we want to show that this determinant, yz, xy, and xz, and then xy, xz, yz, and then xz, yz, and xy is equal to this determinant, y squared no, yz, sorry, yz, y squared z squared, and then x squared xz, and then z squared, and then x squared y squared xy. So I remember when they asked you to show this, we were happy, but immediately a sentence comes after that without expansion. Okay? The without expansion part is actually, could be fun if you are a teacher, but it could be a little bit problematic if you're a student, especially in the exam. So we want to show that this determinant is equal to that determinant. One simple way, of course, I wouldn't say simple, but from mathematics point of view, lengthy calculation is not a hard calculation. The lengthy calculation is...
Are you busy?
Yes, a little bit. Stop recording. So do you have any suggestions for me? You see that you feel that to torture now, yes? Because it is not clear what to do to go from there to there, even though the idea is very much the same. So let me just give you a hint, yes? For example, I start from the left-hand side, hopefully. I take an x out from the... let me just not say something. I write something like this. Do you agree with me? Don't write it down, but do you agree what I have done is correct? Yes?
Yes.
Because I just factored an x out from the first row, and because it didn't have any x's, it's inevitable x goes to the denominator. Yes? Okay, so let me make it a little bit better. So do you understand that one? Now I will write like this. Is that also understandable?
No.
So try to understand. Yes. What did I do? Yeah, I took x from the first row, but y from the second row, and z from the third. Yes? I did that. Is that right or not?
Okay.
Then what? Yes? Exactly. So that was the trick. Now that you have the numbers outside, you have a lot of freedom. You take this one and multiply it here in the column wise. And then you take this one, multiply it here, and take this one, multiply it here. Let us see what happens. If I multiply x on the first column, it generates y, z. It generates x squared, x squared. And if I multiply y here, y squared, y here, xz, y here, y squared. And then if I have z there, z squared, xy. Done. It's much faster than expansion, but the price that you have to pay, you have to be a little bit smarter, yes? So I started from the left-hand side to the right-hand side. By the way, I understand why they try to torture us, because there is no way to understand. There are 10 theorems for determinants. There is no way you have them in your memory unless you use them in action. So you see, this is a simple rule. I hope that you understand this gymnastics, yeah? So if you have a determinant in front of you, you have a lot of freedom of how to factorize or how to multiply back. Yes? You can factor from a row, and then when you have it outside, multiply it in a column. Yes? So this gymnastics you need to learn.
Would this be on the test?
Yes. I need to take revenge, you know?
Oh.
The human society works like that, yes? During your childhood, you develop some obsession or something like that, and you take the revenge, isn't it?
Yeah, of course.
If you forget to write without expansion on the test, can we just expand it?
Yeah, of course. Yeah. Then I am completely following the logic, yes? So if I forgot to do that, but I might give you a 5x5 determinant, then be my guest to do that. Yes. Because this idea is simple if I increase it to 5x5, yes?
Yeah.
But if you want to expand by 5 by 5, so how many determinants are involved? For 5 by 5, you have 5.
120.
You have 5 4 by 4. For each 4 by 4, you have how many? 4 3 by 3. And then for every 3 by 3, you have 3 2 by 2.
You need 5 factorial.
Yeah, it is. It is 5 factorial. That's also a good discovery. Yes. So 120 determinants in principle you have to calculate. Of course, it becomes simpler and simpler because the order decreases. Okay, so let me ask you one more question. What do you think about this? If I multiply my matrix by a minus sign only, and I want to calculate the determinant of that, can you say something specific about this situation? I mean, usually when I ask this, my point is how the old determinant is related to the new determinant. Do you think I can write something in particular or not? Or it depends to something? Yes. Let us ask Rocco this. Yes.
Maybe you could just pull up the minus sign and put it in, so just minus determinant A.
Do you bet your life on it?
No.
Okay. So,
Just yes.
yes, Alex?
I think it depends if the order is even or odd.
Odd. Yes, because I just told you, I don't want you to forget. So let us review. What did I tell you about this? I told you you cannot just simply put R out, you have to raise it to
The order.
and then multiply that, yes? Okay, so this means that this can be viewed as determinant. Instead of a minus sign multiplied by A, I can view it as a minus 1 multiplied by A. Yes? And then if I want to bring it out, I have to raise it to the order, which I don't know, and then multiply it by the determinant, yes? But then there are two cases involved. Because this order might be even, then this becomes simply the determinant itself, if n is even, yes, or minus the determinant. So what Rocco mentioned only works if n is odd. But if n is even, they are exactly equal, yes? Okay. But again, when I say minus 1 by A, I mean minus 1 by all entries, not one row or one column. Be careful about that. For example, I have written some examples here that these are good examples. Let us do them together, okay? By the way, I have used this DET for determinants, but I hope that you agree with me. It doesn't matter if I write it like this. It's similar to absolute value, but there is no matter of confusion because what you see inside is a matrix. So when what you see inside is a matrix, it means that this is determinant, not absolute value. So what can I write for this one? I can write R to the n, the order, and then multiply it by the determinant. So it doesn't matter if I write it in this language or this language, yes? So you need to know both of them. So one example. So what we do, we say that, okay, let I be the I, so let me write it like this. So what do you write for this? Can you calculate this? Determinant of minus 2 times the identity matrix 5 by 5. So you know that when I put 5 here, it means the order is 5. So what can I write for this? If I ask you, what is this?
Minus 2 to
Minus 2 to the power of 5 multiplied by the determinant of your matrix, which in this case is I5. But minus 2 to the power of 5 is just simply minus 32, and the determinant of I5 is? The determinant of all identity matrices is 1. What was the underlying theorem? Yes?
It's a triangular.
Triangular matrix.
Or diagonal.
Of course, diagonal is a specific case of a
Yeah,
triangular
but in
matrix.
that case, then the determinant is just equal to the
Product of the end, yes. And the entries are all 1 by 1, so that's 1. So that's the answer. Okay, a little bit better example. So example, you have the lecture notes, so I don't write them very disciplined. You can see that. So A is a square matrix. A,
Bob, sorry.
yes?
Does it say minus 21 to the power of 5?
No, minus 2. This is brackets.
Okay.
So A is a 4 by 4 matrix. And we know that the determinant of A times A itself, determinant, is equal to 32. And I want to ask, what is the determinant of A? Yes? So how do we answer this question? So I don't want to answer just, I want you to understand these notations are sensible. Is that right? Because I am telling you that I have a 4 by 4 matrix, imagine it in your head. What is this at the end?
A number.
It's a number. Whatever it is, I calculate its determinant, it becomes a number. Nothing prevents me to multiply that number by my matrix. I multiply, it becomes a new matrix. And this means the determinant of this new matrix I generated is 32. Now I am asking, what is the determinant of my original matrix? A. That's a sensible question. First, I want you to understand that, yes? Okay, how do you answer that? Extremely simple.
I think we take out determinant of
Yeah,
A and
exactly,
make it
because
equal.
this is playing the role of your R here. R is a number multiplied by that. I am allowed to take R out from the determinant sign, but the price I have to pay is to raise that number to the order of the determinant. This is why the order is given. So what can I do? Instead of that, I bring this one out, but I have to raise it to power 4. What is left for me? This number is pulled out, the determinant of this matrix is left. And then I have 32. Extremely simple. I have a number to power 4 multiplied by the same number. It means that number to power 5. Okay? And then I have 32. Okay? It's extremely easy to say what is this one. It is 2. Yeah, so these are very good questions for multiple choice questions. So you just can do them quickly. Okay, so another example I have written here, let me also do that. So example, let A be a square matrix of order 4. Let me write it like this again. It's 4 by 4. And we know this. We know that the determinant of 2 times A times the matrix itself is 32 times... Can I write 32? Do you complain if I write something like this? Yes or no?
Yes.
Yes, why?
A is a matrix.
Yeah, it's a number multiplied by a matrix. The result should be a matrix, so it cannot be equal to a number. Okay? So this, if you see this, you feel bad about it. Yes, you should just immediately complain. Yes? Okay. So what you do, I would write an I here. Now it makes sense. Because on the right hand side, I is a matrix. Of course, it should be also 4 by 4. I multiplied by 32, it's a matrix. The left hand side is a matrix. I am saying that these two matrices are the same. Yes? And now I am asking you I want you to determine the determinant of A again. So if I give you this relation and this information, I ask for the determinant of A, what's your answer? It's a little bit more tricky than before, but this is not hard at all. So let me pause a little bit, wait for you, okay? So what happened? At least the starting point is not hard. What do you do if I don't say anything to you? At least you know what to do for the first stage, yes?
You bring out the 2.
So, with which power?
4 by
4. It's 4 by 4. That is easy. So I bring it, so let me write it. 2 to the power of 4, determinant of A, and then A equals to 32i. And then this becomes 16. And of course, you can go a little bit further. Yes? So what can I do?
Divide both sides. by
At least,
16.
yeah. Let me make life simpler, okay? 2i. But what is your suggestion now? Yes?
Maybe we could divide by the determinant of A.
Yes, we can do that. If it is guaranteed that the determinant is not 0. By the way, this is guaranteed that this is not 0. Why?
Because the right hand side is not.
Is not 0. Because if this is 0, this becomes a 0 matrix, but this is not a 0 matrix. So, but what happens if, of course, if I want to follow yours, so your advice, so I will do that. Then what?
So
Or I have another way.
Yes?
So it's determinant of A times A is like it becomes a identity matrix times 2.
Yes?
And we know that the determinant of A should be like every entry to the power of 4. And then if we just choose one entry, then it becomes A to the power of 4 times A should equal to 2.
Somehow, yes. Yeah. But you are making it harder. So I don't know why didn't you take this leap? What I want to do here now. I would say to myself, if this matrix is equal to this matrix, I can guarantee that. What? What? If two matrices are of the same order as square matrices, I can conclude that. Yes? But is it the other way around? No, because we can cook up a lot of matrices with the same determinant, yes? So if this matrix is equal to that matrix, it is guaranteed that this matrix, this determinant, is equal to this determinant. Yes? And then I use it once more. So can I pull this out?
Yes.
Yes, it's a number, but which power? 4. And what is left is determinant of A. Yes? And on the right hand side, I pull 2 out with the power of 4, determinant of I. But then this combine, so you see the answer is not correct. So the determinant to the power of 5, if you want, we can check your answer as well. But this is 16. Yes? Because determinant of I. And then I am looking for this. So it was not possible to easily guess. This is the 5th root of 16. So try to teach yourself, because you got stuck. You need to know why you didn't take this leap. That was crucial for this problem.
So I got 2 to the power of 4 divided by 5.
So it's not yes, correct.
Yeah.
2 to the power of 4 divided by 5. Yes, correct. Because this can be written as 2 to the power of 4 divided by 5. But this is more a straight way of doing things.
Yeah,
Yes.
I did it kind of weirdly.
Yeah. So you need to imagine what is going to happen. I didn't use my imagination. I reserved it for later. Okay. But when I can do it straightforward, I prefer to do that. So that's a good thing to know. If two matrices are equal, if you want to, you can conclude the determinants are the same, but not the other way around. By the way, the other way around is wrong. Yes, we should say the other way around. I have to practice to learn this. So, the other way around is not correct. Yes.
I think it's great.
Anyway, because I recently started reading a book, and that was a British professor, so she's always writing the other way round.
But it's different between American and
Yeah, the other way around is also correct.
Is it correct? Okay, good. Anyway, so I prefer to stop here now, and then you have something to do, you can start working on that. But there are some more interesting theorems come. So might be it's good to think about. So you think yourself, I will not probably be able to prove it rigorously for you, but the question is that if I give you a determinant, I am writing it 2 by 2 intentionally to make writing simpler. Of course, answering it for this case is extremely simple, but we want to talk about the general case. What happens if I interchange 2 rows? Of course, I generate a new matrix. How the determinants are related? Or if I interchange 2 columns, how the determinants are related? It's not trivial.
No?
Okay, I want you to think about it. And then we can go through a little bit of proof of that. But there is a very nice relation. Try to discover it yourself first by giving some examples for yourself to see what happens if you interchange 2 rows only. Just take 2 rows, interchange them. It doesn't matter if they are close together or far away. or if you do the same thing for the columns or rows, it doesn't matter. And there is a reason why whatever we do with columns, we have a counterpart why we can do it for the rows as well, or the other way around. That's also a fairly harder theorem why this works. Yes, we will come to these things later. Yeah. So hopefully we can finalize this determinant, and finally, do you remember why I started talking about determinants? Yes?
To see if a matrix was invertible.
Yes, and if it is, how to find it? We haven't answered that question yet from the previous chapter. We learned about invertibility, but two questions are left open. How can I understand if the matrix is invertible? Not by the crude definition model. Of course, you can have definition. And then if the answer is yes, the matrix is invertible, we didn't address this question, okay, how we can calculate this inverse. At least determinants will actually give one way of doing this, answering both questions, okay? So that is, I hope that we can cover them. I think that would be a good package of what we learned about matrix theory. Yes?
In the example, when you change rows,
Yes?
when you change rows, is the determinant minus of the original answer?
Yeah.
Yeah.
And this is obvious very one for 2 by 2, but when I have a 100 by 100 determinant, and I say choose the fifth row,
Yeah.
and interchange it with row number 97.
Mm.
We want to say that yes, in that case, this will pick up a minus sign only, not that big difference. Yes, we want to understand how. Yes. I just want you to understand how. I don't want you to prove it, because the proof writing it is technical, but proving it is not that. I mean, explaining the idea behind the proof is not that hard, but if you want to write it explicitly, it's a little bit harder. Any questions? Thank you.